Now you must be asking, how do we know that such a fission core or binary casino can split any file? Or let's generalize the question. What rules do we need to follow when creating a fission core so we can be confident such a core will split any file? First, in every row of tables there must always be a combination of cards with which we can synthesize all 2-bit numbers. Basically, there needs to be a way to fission the numbers 0, 1, 2, and 3. Another rule we must follow is to ensure the informational balance in the core. That means we should perfectly distribute input data among the dimensions. That can be achieved by calculating the average bitrate of the table from the bitrate of each card on the table, then finding the total bitrate for each column and each row. Ideally, the bitrates of all dimensions should be equal. You can probably already guess the bitrate of each card. For singles, there is nothing to write to the output file, so the bitrate is 0. Pairs always use 1 bit, so the bitrate is 1. Tuples or triplets have bitrate 1.66 per card. Actually, that is the worst possible outcome for tuples, so the bitrate is actually much lower. And the Joker card has a bitrate of 2. This means the fission core we have been using until now is very well balanced in every aspect. There is a bitrate of 2.66 in all rows and all columns, with the columns being much more important. If the bitrate is inconsistent and changes row by row, it doesn't affect the performance too much. But if the bitrate is inconsistent between dimensions, it will generate fragments of different sizes, which is undesirable for our use case. Another, and I would say really fundamental rule that must be fulfilled is that the total bitrate of the entire fission core must always be slightly higher than its depth times 2. Essentially, the total bitrate of all tables in the fission core must be higher than the bitrate of the input stream. If such condition is satisfied, then we can say the core has a highly positive fission potential. This is logical because on each row we are splitting a 2-bit number and we have to have enough space to store it somewhere. For example, if we omit the dimension of a blue player, then we will be forced to store 6-bit information from the original file to 5.33 bits, which is impossible. Such a core is called a compression core, and these cores rarely work. Since the input is usually an extremely compressed file, typically video, which cannot be compressed any further, the splitting process will hit into a wall and the fission resistance will approach infinity. Finally, here is a recommendation for the counter's starting values. The starting value should not exceed the depth of a fission core times 4. In our case, the core depth is 3, so the largest reasonable starting value of counters should be 12. Smaller starting values are safer and more secure. But on the other hand, by decreasing the starting value, the core's fission resistance increases exponentially. These are probably the most important rules which need to be followed in accordance to construct a working fission core. Well, the construction of fission cores is kind of an art. It is almost like balancing an egg on the tip of a knife. But wait, there is more. Now let's look at a special technique of creating a choke point. A choke point is a place in the game where cards on the table or combination of cards on multiple tables make it impossible for a player to successfully fission 2-bit number. For example, if we have 2 tables next to each other with O, P, and A cards on one table and Q, R, and B cards on the other, then there is no chance to fission the number 0 with this setup, no matter what cards the croupier picks. It is described nicely in this XOR matrix. Choke points are located around the main diagonal, but instead of numbers this time we are performing XOR operation between cards. You may ask, why do we need choke points? Well, this technique is used to create statically or rotationally resistant fission cores. It forces users to use all dimensions simultaneously rather than only one at a time. And this is exactly what we want. For example, here we can clearly see that the user must use all 3 colors to split the file. They cannot do it with 2 and they cannot do it with only 1 color. The user must use all 3. If we dig a little deeper, then it is easy to see static resistance of red dimension directly in the first step. The very first table immediately prevents user from splitting number 2 and number 3. It yields only numbers 0 and 1. Rotational resistance is not so easy to see. We define the rotational resistance of the first degree as follows. Imagine that the tables are not placed in a column, but in a circle. If we duplicate such a circle and spin it, and if we find at least one choke point in every mutual rotation of these two circles, then we can say that the dimension has a rotational resistance of the first degree. The second degree resistance can be defined in a very similar way. We duplicate the circle twice, then verify that each mutual rotation of these three circles contains at least one choke point. And that's it. In the case of this three-dimensional core, the rotational resistance of each dimension is equal to infinity. It doesn't matter how many times we duplicate and rotate the red, green or blue dimension. We will still end up empty-handed. One color is simply not enough to split any meaningful file. With this core, containing inbuilt static resistance, we can see the choke points quite clearly. If the user wants to split the file, he must use all three colors. So, in principle, it is not possible to split a file by using one dimension twice or three times by not using other colors. For example, by ignoring blue and putting two greens side by side. It is impossible. And here you can see it in the video. The original file is being split, it has more collisions per bit, but in the end, it always succeeds and produces valid fragments. Well, now a quick recap. What have we achieved so far? We have together discovered the technology of restricted multidimensional bit chains where users are forced to split file horizontally across the bit stream. By doing this, they are guaranteed to receive free redistributable fragments where anybody can verify the validity of those fragments. And at the same time, if the user receives only one fragment, they do not know what is hidden in it. Most importantly, one fragment on its own does not contain any meaningful information. If the fission process is performed correctly using all colors, then the size of all resulting fragments will be the smallest possible. For example, if the user splits a 1 GB file using this 4-dimensional core, he will receive a set of 4 fragments of a total size 1.07 GB. What is absolutely most important is that user cannot transform the original file into one big fragment of only one color, let's say red one. We want to strongly disincentivize this behavior. You can clearly see it in this example. If the user behaves correctly and uses all 4 dimensions, the counters go down slowly, and in every round the splitting procedure processes 2 bits of information from the original file and spreads it among 4 dimensions. On the other hand, let's imagine a user wants to fool the system and transform all data from the original file into one big red fragment, which is exactly the thing we want to prevent. First, it is impossible to achieve it with the proper fission algorithm. So the user will need to change it by creating some linear variation of this algorithm, and even then it will not work, because when he tries to mimic the behavior of the fission core and transform the input sequence of 2-bit numbers directly into the output fragment, the counters will go down like crazy. There is no chance he will be able to control the entropy. The only way how to transform original data into one big fragment is to use steganographic attack. Steganographic attacks are highly suboptimal, and we will touch this topic later, but for now it is safe to say there is no better way how a user can split the original file and produce a valid set of fragments while maintaining minimal bitrate, other than using a proper fission core and strictly following the rules of the game. But now, we are finally reaching a milestone. It is time to open the chapter where we will discuss cores with one or more redundant dimensions, which can finally allow us to share a digital content, possibly a copyrighted content, without facing legal consequences. And that is what the next chapter is about.